So in this part now we are going to move forward to other properties of the heat transfers like specific heat capacity. Now in specific heat capacity we will be dealing with how different bodies appreciate differently to the heat transfers. So that will be covered by the specific heat capacity. After that we will move forward with the topics of measuring the calorimetry. In calorimetry we will be dealing with how the heat transfer takes place, and in there what are the arrangements that are being ensured so that we can measure the work and the heat at the same time. So let's start. Let's start the new portion called the specific heat capacity, calorimetry and the change of state. Now what is specific heat capacity? The change in temperature of a substance when a given quantity of heat is absorbed or rejected by it is characterized by a quantity called the heat capacity of that substance. Means when we supply a heat to a body, suppose a body is there, we are supplying heat. So when you supply the heat, its temperature will rise, right? Now when this temperature is rising, now there is a parameter that is used to characterize that for the same heat, different bodies will have different rise in temperature, right? Like suppose if you supply some quantity of heat to a vessel of aluminium, and you may supply that heat to a vessel made of wood. So when you apply the same quantity of heat, these two bodies will have different change in temperature, right? The aluminium will go to a higher temperature, the wood will not go to that high temperature. So what is that property that determines that which body goes what change? That property is the heat capacity of that substance. We define the heat capacity, here we are defining it, the S of a substance as delta Q by delta T. Heat is means if you supply an amount of heat called delta Q and the change in temperature of that body is delta T, then S is called the heat capacity of that body. It's the heat capacity. Okay, every substance has a unique value for the amount of heat absorbed or rejected to change the temperature of unit mass by 1 unit. So what will be the heat capacity? When will the heat capacity be 1? It will be 1 when the delta Q by delta T, this ratio is 1, right? So the amount of heat that is changing the temperature delta Q by delta T is 1, then it becomes 1. It's 1 unit. Okay. Now this quantity is referred, when you calculate this per unit mass, then it is called a specific heat capacity. When you calculate means this was this delta Q by delta T. When you find out per unit mass, it becomes specific heat capacity. Specific capital S, which is written by a value small s. Okay, this is small s, this is capital S. When you find out a specific value for anything, now this term you will find in many places in physics. So whenever you have the value specific is always per unit mass. Okay, anywhere whenever it is there, it's always per unit mass, or in some situation it may be per unit moles. But that's what this specific means. It's always the per unit mass of the substance. Okay. Here I have defined the specific heat capacity. If delta Q stands for the amount of heat absorbed or rejected by a substance of mass m, when it undergoes the temperature change delta T, then the specific heat capacity of that substance is given by 1 by m delta Q by delta T. This is 1 by m times your heat capacity. Means whatever is the heat capacity, divide that by the mass of that substance, you will get the specific heat capacity. This is what the specific heat capacity means. So it tells you how fast a body responds to a change in temperature for a supplied amount of heat. Okay. So when you have two body, a body with a high specific heat capacity, what does it mean? It means that the body with higher specific heat capacity means it needs more heat. High S means the numerator is high. That means it needs more delta Q for same change in temperature. So you have two bodies, you supply same amount of heat delta Q. Okay. So for the change in temperature delta T, higher specific heat means body with higher S will require more heat. The body with less S will require less heat. Okay. So that means suppose I have supplied 10 joule to a body of aluminium and a wood. Okay. So when I supply it to aluminium, it will have a rise in temperature and the wood will also have a rising temperature. Now we know that aluminium has higher rising temperature, so that means it has lower specific heat capacity, right? Because it's very simple to see, this is aluminium, this is wood. Okay, you supply heat 10 joule, you supply the same heat 10 joule. Its temperature will change by 20 degrees Celsius, suppose, and its temperature changes by suppose 5 degrees Celsius. Okay, which is higher specific heat capacity? This body, because delta Q is same, delta T is smaller for this. Delta T is only 5. For this, it is 10 by 20. Okay, so when you are comparing delta T, since this is denominator, lower denominator, higher values. So this will have high specific heat capacity. Now water, it has a specific heat capacity of 4200 joule per kg degree Celsius. Now you can find out the unit from here, right? Delta Q is energy, so it is joule per unit kg per unit temperature. So water has this value 4200. Now since this value is very high compared to all of this aluminium, steel and everything, this water has a highest specific heat capacity. That's why it is used as a coolant. Coolant means for cooling things. Now since it has a high value, what does it mean? It means that even when you supply very large amount of heat, the change in temperature is very small. Means when you supply 4200 joule, then there will be a change in temperature of 1 degree Celsius for a 1 kg mass. So for a body with 1000 specific heat capacity, joule per kg unit per degree Celsius, means only when you supply 1000 joule you will have the same change to that body. So a body with 1000 joule per kg degree Celsius needs only 1000 joule for 1 degree Celsius rise in temperature of a 1 kg mass, but water needs 4200 joule. So when you apply 1000 joule to this body, this temperature won't be 1, it will be quite less than 1 degree Celsius. So it is used as a coolant. Sorry. Calorimetry. Calorimetry is the measurement of heat. How do we measure this? Flow of heat. Heat is the energy in transit when it is in motion. How do we measure that energy? That is measured through a process called calorimetry. When a body at a higher temperature is brought in contact with another body at lower temperature, when you connect two bodies of different temperature, heat will flow. So the heat lost by the hot body will be equal to the heat gained by the colder body, provided no heat is allowed to escape. Now a device which will ensure this, that when you bring two bodies in contact, one hot and one cold, heat flows from hot to cold and no heat is lost anywhere else. That has to be ensured. So then only you will be able to equate this, right? The amount of heat lost is equal to the amount of heat gained, because the energy is, total energy is always constant. Suppose if you are losing some energy to the surroundings, then you cannot apply the equation, right? Because the amount of heat lost by it, part of it is gained by the body and part has been lost. So you cannot equate these two values. So you need to ensure this. Now this is ensured through a body called calorimeter. That ensures this. I will draw the diagram for this, what kind of this body look like. It consists of a metallic vessel and a stirrer of the same material like copper or aluminium. The vessel is kept inside a wooden jacket. Keep this vessel in a wooden jacket which contains heat insulating material so that no heat goes outside. The outer jacket acts as a heat shield and reduces the heat loss from inner vessel. So let's draw a diagram to see what kind it looks. You have a body like this. Then you have this insulating cover. Sorry for the poor drawing. That's why scientists have defined a word called schematic diagram. Means it only shows you the scheme. It's to hide the poor drawing abilities of the people who study science. So this is a schematic diagram. It only shows you the scheme. So this is an insulating layer. It could be made of wood. It could be made of wool. Anything. And this covers it totally so that no heat is being lost from this. Now this is air. Now air is a poor conductor of it, so there won't be any conduction. That is to ensure this. Now this is a vessel. Okay. Then you have a thermometer that is kept here like this. and you have a stirrer. Stirrer is like this. Why? What is this stirrer for? When this rotates, when this stirrer rotates, it will rotate the liquid that is kept in this. There is a liquid that is kept here. So that means you are doing some work. That work is being lost and the temperature of the water rises. Now, Joule, he used this experiment for the first time. What he did? He did some work on it. By rotating this, he is doing some work. Suppose he did 10 Joule of work. Okay. Owing to this work, the temperature of this water body rose. This water that is kept here. So he equated this work done to the temperature rise, right? Because there is no heat being lost to outside, right? It has been ensured that no heat is going outside, that is calorimeter. So now whatever work is done, that must result in the rising temperature in this thermometer, right? So then he equated in this. So this kind of system where you ensure that no heat is being lost to outside and you measure the transfer of heat, that is called calorimeter. Now there is an opening in the outer jacket through which a mercury thermometer can be inserted into the calorimeter. This is this arrangement that we are talking. I hope this is clear. This is air to ensure that there is no transfer from this, and even if there is some transfer, this is a wood, made of wood, so there won't be any transfer to the outside. I hope this system is clear how it is ensured. Okay. Now this transfer of heat, this could be through any other process, like you may have this system and then you may have a hot body and a cold body. This is a hot body and a cold body. So what you do is that you bring these two body within a calorimeter. Suppose this is a calorimeter. So what happens is that this body ensures that no heat is being lost to outside. That means whatever heat this loses is gained only by this. There is no other body that can accept the heat, and there is no other way that will through which the heat can go outside. So this can accept it. So whenever you have questions like this thing is done in calorimeter, it only thing that it means is that the heat is not escaping outside. But what may happen is that this body may be made of like copper or aluminium or anything. So this body may see a rising temperature, right? Because the heat is being lost. Now this heat may be accepted by this body, right? If it is made of wood, there won't be any appreciable change. But if it is made of copper, aluminium, this body will also absorb it. But what is the thing, what simplifies our problem is that we know what will be the change in temperature of this material, right? We can measure it. So if you see that there is a change in temperature of 5 degrees Celsius, if it is made of copper, you will have the specific heat capacity of the value. Then you can find out that whatever is the heat lost is the heat gained by the cold body plus the heat gained by calorimeter, right? This new term will come because now this is a measurable quantity, right? So you can, from the total heat lost, you can subtract this value and that will be the energy gained by this cold body. So in that case also you will be able to identify this transfer of heat. Okay. Let's see an example here. A sphere of aluminium of 0.047 kg placed for sufficient time in a vessel containing boiling water so that the sphere is at 100 degrees Celsius. So this statement tells you that you have an aluminium sphere of 0.047 kg such that its temperature now is 100 degrees Celsius. It reaches temperature of 100 degrees Celsius. That has been ensured by doing this, putting it in a boiling water for sufficient time. It is then immediately transferred to 0.14 kg copper calorimeter. So that means now you have a calorimeter of copper that is containing 0.25 kg of water. So you have a water here. This is calorimeter, this body. That means no heat is going outside. So this is water 0.25 kg. And this thing is put here in this water. Okay. The temperature of the water will rise, right? It is at 100 degrees Celsius. And this is water is at 20 degrees Celsius. Right? It is given to you. So the temperature of the water is, will rise because it is at a higher temperature. It is in contact with the body at higher temperature and attains a steady state at 23 degrees Celsius. When you put this into this, the final steady state means steady state is a state when there is no change in temperature, no further change in temperature is happening, right? Everything has come to a still state. Now there is no transfer of heat that is taking place. At that point the temperature is 23 degrees Celsius. You have to calculate the specific heat capacity of aluminium, means this sphere. Now if you see in this question, it's given that what is the mass of the copper calorimeter, but the specific heat capacity is not given, and also the change in temperature which is not given. Now you may argue that I will take the change in temperature to be this same 23 degrees Celsius, right? Because all of this is a one system now. So when there is a steady state, you can always assume that all of the bodies come at the same temperature, means you can take that calorimeter comes at 23 degrees Celsius. So that is a fine argument that you can always take. But the problem is that you don't have a specific heat capacity of copper here. Since you don't have the specific heat capacity of the copper, you cannot find out this heat gained by the copper, right? What is the heat gained? If you remember, we know that delta Q by delta T 1 by M was specific heat capacity. That means delta Q is sorry, M into S into delta T. That is the heat transfer. Okay. So now when you put this aluminium sphere here in this water, its temperature goes from 100 to 23, right? All of the bodies come to 23. So what will be the heat lost by the aluminium? This will be mass of aluminium, specific heat capacity of aluminium into delta T. What is delta T? It is 100 minus 23. This is the heat lost. And what are the things that are whose temperature is changing? The water. The water is of mass 0.25. It is going from 20 to 23. So write the heat gained by water. It will be ms delta T again. So mass of water is 0.25. S of water. Now specific heat capacity of water, you should always remember this value. It is 4200. Delta T. What is the change in temperature? It's simply 23 minus 20. Plus the mass of copper into a specific heat capacity of copper into change in temperature of copper. Now since this is not given here, in this situation I am assuming this term to be 0. I am assuming that all the heat is being taken by this just because it's not given. So whenever this value is given, use this whole formula that I have written. Okay. So now see what's happening here. Mass of aluminium, it is given to you 0.047 into S. This is what you have to find out of aluminium. Delta T is 77, right? 100 minus 23. This is 0.25 into 4200 into 3, 23 minus 20, right? Solve this, you will get S is equal to 0.25 into 4200, you can write it 42 into 25 into 3 by 77 into 0.047 means 47 into 1000, right? Now here you have to solve it. What we do is that this 42, 47, I'm doing a very approximate calculation. 25 into 3 is 75. So I'm cancelling 75 with 77, not exactly. In the exam you have to use the calculator to find the actual value. And 42 with 47, the value comes out to be approximately 1000. Now since you can see here that the denominator is greater in both of this value, right? 42 cancelling with 47 means you'll have 1 point something here, again 1 point something here when you can cancel with this. So this value is actually less than 1000. Actual value of a specific heat capacity will be less than 1000, which will be the answer, the actual answer. So here we saw what exactly is the specific heat capacity and how it differentiates between different bodies based on the heat transfers and their reactance to the heat absorbance. Later on we are going to talk about what exactly is the latent heat and how the heat does not appear in the form of temperature when there is a change of state. So stay tuned to Ask IITians for more on this.